This talk is about verse concurrency, which, as you guys may have come to realize if you've been fooling around with the Unreal editor for Fortnite, it's kind of everywhere. So one of the reasons that I thought this talk would be especially good is whenever we make features with concurrency or the language, we'll often have documentation that will describe each individual feature, but not often how they work together. So this is to get you more ideas of how to use the different sort of concurrency constructs together. So this is me. Verse is the fourth game programming language that I helped create. And there's all sorts of concepts that evolved over time that finally made its way into verse. So the concurrency aspects are probably the most evolved and the most sort of stable aspects of certain ideas that I've seen how they work over time. And so they are pulled from an earlier language I did called Concurrency, which some of you might have heard of. It was hooked up to Unreal. Anyway, so with verse, one of the ideas is that rather than describing little bits of things, it's more of a stage direction, in that you can say, you know, the bad guys should be over there, and somebody runs over here, and cue the music, and it's like directing a play or something like that. So in traditional game development, you're usually describing a single instantaneous moment of time, and you update with a on-tick or an update or something like that, and you describe every single thing that's going to be happening within that instantaneous moment of time. And you have to keep track of state, because as the game changes, your update, you know, you're going to be updating different things, but you have to have like big switch statements and, you know, keeping track of where you are. But with verse, it's more you describe a flow of time, and you don't have to worry about necessarily constant, you know, iterating and looping of a single instantaneous moment. You have a progression of your missions, your game, and certain things that can be happening at the beginning of the game, you don't even reference anymore, just because, just like the flow of logic, you're doing the flow of time, and you know, you progress along in your game, and you know, different things are happening. And I have found, like, my background is cognitive science, so I'm always trying to figure out what people are getting stuck on and what people do understand. And trying to describe a single instantaneous moment of time is not a very intuitive way for the human mind to grasp at things. But describing things in terms of flow of time is much more intuitive. So before I get into some of the details, I thought it was important that I just go over some of the basic stuff so that it makes sense of what I'm talking about. Hopefully you guys maybe know a lot of these things already. So when you are talking about individual time flow expressions within verse, we differentiate between things that happen immediately and things that we call async, things that can actually take time. So the actual way you do time could be based on events. It could be things that are happening over time. It could be, you know, doing all sorts of different continuous work or some combination of events and work. You can set it up however you like. But one thing that's important to know is whenever you have a bunch of commands that are immediate, like adding two numbers, adding something to an array, or whatever like that, all those things, if you have a bunch of them one after the other, they're all grouped as a single unit, so they can't be broken in half. So if you like start some process and then you finish the process, it's not going to break in the middle of, you know, doing those things. So like with traditional time flow programming, you usually have to put semaphores around things and make sure that, you know, critical sections and stuff like that. But with verse, you don't have to worry about that, because if you do a bunch of different immediate commands, they're just automatically, atomically grouped together as a single unit. And to define functions that are async, you just specify the suspends qualifier, and you can then just call it like any other function. And they look identical to regular functions. But the body of a function that is async will allow you to call other async expressions. So this is sort of everything in one picture in terms of a lot of the different concurrency commands. So this is what we call structured concurrency. So there's structured logic, like your if-thens and loops and things like that, that stay within a given scope. So structured concurrency is the same thing. The scope of all of these commands stay within the scope of a given async function. They will not leave it. So like a goto, you could jump all over the program, so that's why we generally, that's called unstructured, programming, but this is structured concurrency, so it's structured time flow. So a block command does everything in serial, one after the other, so it'll continually do that. We often call, another name for an async function is a coroutine. That's sort of common in the industry. It's a little bit different than coroutines in a lot of other languages, but just for using a common terminology, we often call them coroutines too. So that coroutine one, it will do everything it needs to do to completion, however long that takes, and then it does the next one, and then the next one, and the next one. That's block. And with sync, each of those things goes to completion, but all simultaneously over time. So you can see the little arrows representing each of their different times. And then it won't go to the next expression until they're all done. And then race, sort of like sync, they all go at the same time, but whichever one completes first, it wins the race, and all the other running sort of sibling expressions are canceled before it does the next expression. So with rush, it's very similar to race, except when the first thing completes, you go to the next expression, but everything else that didn't win the race keeps on going. But you notice there's that little red line here. This is the thing about rush and branch that's sort of special. So like I said, it's structured, so it stays within the time frame of a async function. So if these things, if their lifetime, if they last longer than the function that they're in, they'll be canceled because they're constrained to the lifetime of an async function. So that's a little bit of a sophisticated thing. So I often recommend to people, do not use rush unless you really, really know what you're doing. Generally, you can always use block, sync, and race to do what you want. So branch, it's like a block in that each of the different things go in order, except that it immediately runs the next expression as soon as it starts. So it goes off and does its thing and takes however long all these, one after the other take, but you immediately go to the next expression. And they just take as long as they take. But again, just like the rush, if the function that you're within ends before it's done, it'll just be canceled wherever it is. So if you had a branch and a bunch of code, and then it was like the end of the function, and this was all that was in the function, basically nothing would happen. So the other thing to consider is each of these different commands, they all have a result. So inverse, everything that you have is an expression, and every expression has a result. So for a block, the last expression in the block is whatever it had as a result is automatically returned. For a sync, it returns a tuple of all the results of all of its sub-expressions. With a race, it will return whichever one of the sub-expressions finished first. Same with rush. And branch, because it continues immediately, it doesn't have any result because it's possible, you can't know if it's going to even return. So like I say, doing time in verse is basically just like logic with Boolean trues and false, but it's with time. So with a sync expression, it's just like an and. So if you have a whole bunch of different things that are happening over time, it will not go to the next expression unless they all each one of them complete. They're all true. They all succeed. And then it will go to the next line. So with race, it's like an or. So it's saying, I'm doing a whole bunch of different things at once, but whichever one of them completes first, it wins it's sort of the exclusive or, and it goes down to the next expression. So that's an important thing to think of. It's just, it's really easy to add in things that are going simultaneously, and you just have to think of it almost like logic. So I always think it's important that even if you have everything nice and structured and everything works in a nice, perfect way, it never actually happens. So it's good to have an escape hatch. So there's this one command with concurrency called spawn that doesn't obey staying within a given scope of a function. So with spawn, you can spawn an async function or coroutine, and it can just last however long it lasts. It doesn't care. It can go beyond, wherever the scope it was where it was created. It's supposed to actually allow you to have more than just a single coroutine. Like you could have actually several expressions, but we just haven't had a chance to do that yet. Anyway, and so if the scope that you're in is ended, it doesn't matter. It keeps on going. And the other thing that's interesting about spawn is it returns a task. So we call the sort of a time flow path a task. And so it returns one of these task objects to you, and it's got an await command on it. So even though you've launched it and it's going to take however long, you can, at any other point in the code, say that return task.await, and it will sit there and block and wait until it's finished, and then it will go to the next line. But one of the interesting things about that is that you can use that in multiple places. So you can sort of spawn a hunk of code, and it's taking time, and you can say that task await, that task await, that task await, in a whole bunch of different places. And as soon as that code is done, they all wake up. So there's lots of other things in the API that are often used with those sort of main concurrency expressions. So there's using them with each other, of course. So using block, sync, race, et cetera, all within their own sub-expressions. But there's anything else that allows for a block of code, like loops, like for, like case. I forgot if. And if. So another command that I'm sure you've seen everywhere if you've done any verse programming is sleep. And with sleep, it actually has essentially different modes based on the kind of numbers that you pass to it. So if you pass it something that's less than 0, it immediately returns. It's an immediate call, and it just immediately goes to the next line, basically does nothing. If it happens to be 0, it will wait for one server update, which is about 1/30 of a second, right? So, and that's not what is updating on the client. The client and the server update at different rates, which is something that gets people all the time in programming verse. Because if you're trying to do something that's updating at the same rate as the client, you can't do that with the sleep because it's going at the rate of the server. And the server is actually updating slightly slower than the client. The client, depending on your video card, depending on what's going on, it can be faster or slower. If you happen to wait infinitely, it's basically a command that says never return. It just goes into the sleep and it's stuck forever, which sounds crazy, like why would you ever want that? But there's lots of reasons when you would actually want that and it would be good, which I'll go into. So then there's this event class, which when you create it, it's a way that you can do sort of event signaling between different sort of time flow tasks. So with it, you can make one, and then you await in many different locations on it, and everything will be suspending, waiting for it. And then when you signal, all of those things that are waiting on that one event wake up and continue to the next expression. The other thing that's interesting about event is that it's what you call parametric, meaning you can actually say that it's based on a given type. So say you're waiting on, I don't know, you made your own kind of a trigger region. Like, so you made some simple radius-based thing, and when you go walk within the radius, you want to say that a given character, a given agent walked within an event, you could send along which character as your signal, and then all the awaits that are waiting on it would return the actor that you passed. You don't have to have a type. You can just signal it and it'll just wake up, or you can specify a type to sort of pass along. And it will be passed along to every single await that's on it if it's got multiple. So And again, anybody that's been doing any programming with verse should know that the main sort of entry point for verse is the on-begin of devices, for creative devices that you place in your level. And of course, any other suspends functions that are in the API. Right now, there's not that many suspends functions in the API, but there's a few, and you can build up your own crazy suspends functions, because any suspends functions can be used to create other suspends functions. So when you put all those different pieces together, that's what I call sort of stage-based programming. So like I was saying, it's stage directing, is more how you do things in verse. So this is stage-based programming. So one thing to always remember is race is a superpower in that it will cancel all the other things that didn't win the race. And canceling things is a really important aspect of verse concurrency. So one example I often use is, say you were doing all sorts of crazy complex things that were taking time. Normally in game development, you'd have to put in all sorts of hooks to know when something else is happening that you should stop your complex thing, right? Like, I use the example of a volcano because it's going to explode. So with a volcano exploding, traditionally you'd have to say, is the volcano exploding? No? Okay, do some stuff. Is it exploding? No, do some stuff. But with verse, you don't have to do that. You just do your whatever, like I just used the example of explore and escape the island, and however complex and however long that is, and it doesn't need to know anything about that there's a volcano that it's going to explode. But then you race it with, volcano countdown, and when it, elapses, the volcano explodes. And then because it's in a race, if that won, the action of exploring and escaping the island, it's canceled, and then it does whatever the volcano countdown does, right? And then, I just used the example of everyone dies. And one of the other things we talk about in terms of grouping different things together. So here's a race, and you could have just individual async functions that the race is comprised of in terms of its sub-expressions. But often you'll want to have a few things grouped together. So in this case, I just wanted to group together volcano countdown and everyone dies, so I just throw that in a block. And so they run serially. So it does this and then this, right? And so that's a really easy way to group things. If you wanted these two things to run simultaneously, this would be a sync, or whatever else. So like I say, so in terms of using these things all together, so there's all these different existing concurrency functions, expressions. There's all the other flow control things that have blocks of code that you can have into it. And then there's the more, these things that sort of go beyond their call and they can keep on going, but you just want to keep track of when the first thing started, or you just want to start something and keep on going. But one of the other things that is sort of interesting, and I'm going to start flipping between my slides and some code examples, because crazy things have been happening last week, as some of you may know, and I was hoping to add them to my slides, but instead I've just got them in the code. But at least the code works. So one thing that's interesting is if you pass a bunch of async calls as arguments to a function, they work serially. So it'll figure out that one argument to completion, and then it starts the next argument to completion, and then the third argument to completion. But if you want to have them all run simultaneously, it's concurrency, why not have them all run at the same time? What you can do is you can actually use a sync to group them together. And I'll show you what that looks like. Right, okay, so I made this. These are sort of very example commands. I wouldn't necessarily think you could have things in code, but I'm just using them as an example. So this little command, move to, it's specifying 2 points on a map to move to. Move to 1 point, and then when it's done, move to the next point. And then it returns the point that was the second point that you got to. So here, it's calling another thing, another prop that I'm moving. I'm moving like 3 different props here. So the first prop would move to its 2 points, and then it would return D. And then the second prop would move to D and then A and return A. So this prop A would then do its move to G and then A, right? So serially, one after the other. But if you wrap those two commands in a sync, just like with any other sync, it does these two things at the same time. So prop B and prop C will move exactly at the same time, and then when they're both done, then this move to is done. So, if prop B and prop C moving took approximately the same time, with the sync, it'd be half the time rather than doing them one after the other, if that makes sense. So, then there's the defer command. So with defer, it's really interesting in that, so with verse, there is no destructor for classes and things like that. So it's often good to be able to clean things up when they go away. And that includes concurrency. So if you are doing some complex action and you really want it to do something, if it happens to be canceled, the way that defer works is it's called whenever you exit the scope where it was placed. So that includes concurrency. So if concurrency is exited, if it's canceled, and there was a defer hanging around, it will run it. So I'll show you some example of that. So let's see. So this is example code. It works, but I don't know if I'd recommend using it and all sorts of stuff. But this is just basically making a, for any given prop, it will move to a specific positional target. So, and things that are positional are like agents, props, anything that's pretty much got a transform in it, a position and a rotation. And if your target is moving over time, it will keep on moving towards it until it actually gets to it within a certain arrival radius. But the thing is, I'm basing this command on this move to command. So with the move to command, it's not smart in that if it's ever canceled, it just keeps on going. So if I said, move from here to here, but midway through, I cancel the command, the engine doesn't know that, so it just keeps on going. So if I really wanted to have it so that it was canceled midway through, because the whole command, this move to position was canceled, I put in a defer here that says if I basically haven't already stopped because I've arrived, then tell the prop to stop. So I'm going to risk it and actually show an example. So, okay, so I got these little floating props in the air here. This example is not dressed up. It's just total, I've just hooked up basic buttons just to be able to show things. So if I say all these guys move towards me simultaneously with a sync, I can say stop, and they knew to stop their move tos immediately, right? Or I can say, like the block with moving them one at a time, I can say do that one at a time, so each are doing one at a time. But again, I can just say, you know what, stop. I can say reset, whatever. Or this one, like again, just an example of a race. They're all moving towards me here at the same time, but as soon as the first one gets there, they'll all stop because one of them run the race, right? So anyway, but the thing that I was trying to show off is that they actually stop because of that defer. So then I don't have an example of this, but when you create a local variable within a async function, because all the other concurrency calls in the function are in that scope, just like with if-thens and loops and things like that. If you make a variable earlier in your scope and you use it in your loop or your if-then or whatever, it's around. So if you say a command that is a concurrency command and you say, do these different sub-expressions simultaneously, and they had a variable that was defined before them, all those different sub-expressions can all refer to that same variable. So even if you've got so say you had you run over there, and you run over there, you run over there, they're all running, and it's all simultaneous, you could have some indicator of where you should go to, like so you could change the target or something like that. And each one of those things would know to you change where they're going to if you changed it because they're all sharing that same variable. So usually whenever you're doing programming where it's the old way of doing it, where it's an on-tick or something, you would have to take the information that you want to share across the different things that are running simultaneously and stuff it up in some commonly accessible object. But with verse, you don't have to worry about that because it's just, if there's a variable that they all have access to, then they can just access it and use it, and they can all communicate through just variables. There's no semaphores and mutexes and all that kind of stuff. It just works. So when you are when you're doing concurrency, it also makes a lot of sense often to loop over things. You want to do something, and when it's done, you want to do it again and again and again. And so usually when you're programming, if you've got an infinite loop, that's a bad thing. But with concurrency, a lot of loops never actually have an exit, never have a break out of it or return out of it. But with race, because race will cancel things that are going on forever, that's usually the way you get out of infinite loops. So each loop will expect there to be at least some sort of async call within it, so it knows, okay, it's not just gonna run forever within a single frame, within a single update. So it makes sense to, with a race, so like say you said, I want a bunch of things to happen at the same time, but I want one of the things to stop everything else if it ever completes. But a few of the things in the race, maybe you don't actually ever expect them to end ever, and that's perfectly fine. It's just the thing that could end will end, if that makes sense. And so the other thing is when you are doing all these different concurrent calls, it's often the case that you will do a sleep or some other command that takes time, and you spread different work over time, right? So somebody yesterday was talking to me about their project where they said that they did this sort of complex test on one of the players that would be in their game. And it was fine when there's like 5 or 10 or something, but then they got to a point where they'd have 100 players in their game, and they're all doing this test. And it started to get kind of boggy, right? So I said, well, is the test something that is at human speed, or as in like if I step here and then something happens and you notice it as a human, or if it's something that is, if you're rendering something and the flow of the movement must be perfect or it looks weird. And he's like, oh, is this something to trigger for a human? I said, well, then you can make it so your tests that you're doing on each character can be spread out based on how many players there are. So you could have it so that the test that is running in the loop, instead of it doing every single server update, you could have it be every single certain slice of time based on however many players there are. So the more players there are, you could wait longer between intervals. So it would always be doing the same number of tests, no matter how many players you had. It would just be doing the tests less frequently if there's more players. And for most people viewing, it would just seem the same, except you're doing it less fine resolution if there's more people. And I don't know if you noticed, but I'm progressing in terms of using things from, you've got your shark, you've got laser, you got a shark laser, you got a robot shark laser, right? So it's using everything together, right? So all these things are way more powerful when you use them together. So this is debatable, but I'd make some different recommendations in terms of how you use some of the things together. So when you have a bunch of event-based things, like in verse, we'll often have events that have an await on them. So it's an event that's not doing any work, it's just sitting there, and when it triggers, a button press, or you walk into a trigger region or whatever, that event will release the await that's on it and go to the next line. So when you do that, when you're waiting on something that takes time, and you have a bunch of them, what people will often do is that these are all things I want to loop on, right? I want to wait every single time that happens, every time you step into that trigger region. And in traditional logic programming, you're doing a bunch of things and they're all in a loop, well, put them in the same loop. But that doesn't always make sense with concurrency, because if each one of those things has a different amount of time that it takes, if you loop them, even if they all run at the same time, you're still waiting for the longest one to loop. So if one of them triggers really fast, but you're still waiting for something else that takes a really long time, then you're not really looping on a per event thing. So rather than looping a whole bunch of these different time-based things together, you would say each thing would have its own loop, so that there would be a much tighter sort of flow of observing it and watching what it does. So another thing I've seen in people's codes from their examples is they will, when they don't realize that things like await or other async functions will suspend until they're done, they will often just put them one after the other. And so, and then they'll be surprised that, like, I did all 4 of these things I was waiting for, but it seemed to take a really long time, or the second thing wasn't registering when I was pushing it. If you put them in order, it's serial. So if you say, I await the button, I await the trigger region, I await, I don't know, I get near to some other character or something. So those are 3 things that could trigger the same thing, and people just put them one after the other, then you're just waiting for the button, and the other things aren't even being looked at. And then when you push the button, then it looks at the next 2 things. And then if you go into the trigger region, then it waits for being next to the guy that you're near. So you have to make sure to wrap those sorts of things into something like a race. If you're like any one of them, like I say, the logical OR, could trigger the thing that you want to have happen next. Or you want them all to happen, like so it's like a team thing. So someone has to push the button, someone has to be in the trigger region or whatever before the whole thing triggers. Or you have to just go do each one in succession, but it doesn't matter which order, and then they'll all be done. So they all and must be done, so it's a sync. And the other thing is, with those events that are in the system, in the API, you can often subscribe to them, or you can call an await on them. And I often recommend that you use await rather than subscribe. Because with subscribed, it's sort of the old sort of traditional way of working with things, in that if you subscribe to something, it will call something whenever it triggers, but it will keep on calling it. So if it's something you only wanted to do once, you have to keep some sort of handle onto the thing you subscribe to and remember to unsubscribe. Whereas with await, if it's a one-shot thing, you just wait on it once and then you're done. If you want to loop on it, you can just loop on it. But if, say, then you wrap a bunch of things, like I was saying, say you have this complex behavior of you navigating over an entire world, and that's your whole behavior, and some of the things in that behavior are awaiting on things, and then you wrap a race around it because the volcano is going to explode and you want to cancel, then the volcano just cancels it and you're done with await. But with subscribe, if you wrapped a volcano and a race around that complex behavior and things inside of it are subscribed to stuff, they won't unsubscribe. You have to remember all the different logic to make sure that not only are you triggering the volcano, you have to know of all the different subscribes that are going on to stop them. You can you can combine a subscribe with a defer, so that whenever you call the subscribe, you can pair it with a defer, so the defer will run if you cancel the whole scope of where the subscribe was. But it's a bunch of extra work, and it's really easy to miss. So things will keep on triggering when you don't want them to, and you have to write a whole bunch more code. Whereas with the await, you don't really have to. You do have to sort of often wrap it in a loop if you want it to keep on going, whereas a subscribe will keep on going. But still, I think if you get used to using await, I think it's generally more powerful and you can do more things with it. And it's easier to add on to. So the other thing I mentioned, be careful about using rush and branch, because it's got that sort of weird silent, if it comes to the end of a function and they're still running, it will nuke them. So that can be exactly the behavior you want, and because that is sometimes the behavior you want, they exist. But lots of people use those commands without realizing that that's what they might do, right? So I would say be really careful. Almost every single time I've ever seen anyone ever use rush and branch, I have found that they could use sync and race instead in a way that was actually more sensible for what their logic was. And the other thing I would say is when you're building up your game logic that is time-based, the way that you best do that is think of it from a very high level, so that you basically describe the pseudocode of your game and your logic, and you make some names for each of those different sort of major things, and you add syncs and races and blocks and things like that to group things together, and then you just put in the contents of each one of those major sections of your game logic, and then bam, your game is done. I've had a number of different people that were making their game logic, and they were doing things that was very on-tick, sort of update way of sort of constructing their game logic. And then I would help them, just like I say, just making pseudocode and wrapping them in appropriate async expressions. And then their whole game logic looks like pseudocode, but it actually works and it runs. So when you're then trying to improve stuff, it's so easy to see where the flow of your time is going. So, and that's basically it.